All right, so I'm going to work this key for, I guess this is exam 1, 2021, fluid mechanics, fall, all those things. Okay, so I'm going to try to work a lot of this in blue. If I need another color, obviously I'll steal the other color. But okay, student ID number 1, 2, 3, 4, 5, 6, 7. I don't want your name. Some of you probably gave it to me anyway. I'll take a half a point off for that. I want to grade without names. Okay, it just makes things easier for me. Okay, so let's get into these true or false. A fluid with a negative gauge pressure will cavitate. All the negative gauge pressure means is that the pressure is below atmospheric pressure. It doesn't mean it will cavitate. So this is false. It should be like if the pressure is less than absolute equilibrium vapor pressure. Equilibrium vapor pressure. That's what it would need to, okay, which is almost always way below the actual, way below the atmospheric pressure. Okay, the force of pressure on a gate in a static fluid is equal to, okay, let's see, you should be able to remember this, right? The force of pressure is equal to, well, usually it's the pressure, it could either be P bar, which I prefer, pressure of the centroid, times the area, right? Or it equals gamma times the depth of the centroid times the area, right? So it's equal to the pressure at the centroid, yes, multiplied by, not the depth of the centroid, the area of the gate. Okay, so this is also false. Okay, rho on gamma equals G. Well, let's see what we remember. Gamma equals rho times G. Okay, so this is false. Algebraically, these are not equivalent. So this is going to be false. All right. The capillary rise of a fluid in a cylindrical tube is higher if the tube is narrower. And you should remember this from the derivation, but you can also kind of do a little quick derivation on the side if you'd wanted to. You could think about it like this, and you could say, okay, well, the weight is going down, and the weight goes as, it goes as the volume, so that's radius squared times the height, right? With some kind of constant in front of it or whatever, some pi's and some other things. But the force upwards, right, it's going like this, and it's being controlled by this length right here. So the force upwards, right, it scales as radius, right? So the narrower you are, okay, this is going to get smaller faster. And this is going to get smaller, the upward force is going to get smaller as the radius gets smaller but this is going to get way smaller because it's got an r squared. Okay, so this is true. If you don't believe, if you'd forgotten all about that and you hadn't really thought about it in those terms, you can always just derive the full equation, or you could just look through your equation sheet, and there's a section in there called, hold on, let me see if I can find it real quick, surface tension and capillarity, and it actually has the formula, H equals ... and it's got the diameter on the bottom. Okay, so that's how you would know. Okay, so that's true. Hydrostatic force on a gate depends in part on what fluid it is submerged in. Okay, so here's the hydrostatic force on a gate, right? And that gamma depends on the fluid that it's submerged in, so that's true. Okay, for a hydrostatic incompressible fluid, pressure increases linear with depth. Well, that's the hydrostatic law. So that basically says dP dz equals negative gamma. Okay, and that only applies for a hydrostatic incompressible fluid, so that's true. Liquids tend to have a higher bulk moduli of elasticity than gases. So that's basically asking you, are liquids harder to compress than gases? And the answer is true. Yes, they are. Okay, for a gate oriented horizontally, the force of pressure acts at the centroid. So if your gate is like this, okay, then your pressure over that thing is evenly distributed. So when you want to act where that force acts, you're going to put it right at the centroid. So that is true. The specific gravity of a fluid is the ratio of the fluid's density to that of water. Well, that's the definition. Okay, S equals rho over rho water. A fluid cavitates when the pressure of the fluid is higher than the equilibrium vapor pressure. It is when it is lower than equilibrium vapor pressure. This is false. Okay, so 3 falses, 6 trues, and 1 false. Okay, now we're going to go down here. I'll pause this video here and there as I do these, as I talk about these. These are really quick. I wanted these to be quick. I wanted them to be easy. There's not going to be a lot of partial on this particular problem. So let's go ahead and do it. So weight, well, let's see here. Cylindrical tank of methanol has a mass of 80 kilograms and a volume of 75,000 cubic centimeters. Determine methanol's weight, density, and specific gravity. Okay, weight, density, and specific gravity. Okay, so in this case, the weight, well, they give us the mass, so this is pretty easy. Mass times gravity, weight equals 80 kilograms times 9.81 meters per second squared. So the weight equals 80 times 9.81. So that's 784.8 newtons. And then for reporting purposes, I would want you to write weight equals 785 newtons. Okay, 3 sig figs. All right, so then the density. Well, the density is defined as mass per volume. Those were given. So rho equals, the mass is 80 kilograms, and the volume is 7,500 cubic centimeters. So rho is, well, 80 divided by 75,000. Okay, and that's kind of got the annoying answer of 1.0667 times 10 to the minus 3 kilograms per cubic centimeter. Okay, and so, what would I want for this? Well, you could either have written down rho equals 1.07 times 10 to the minus 3 kilograms per centimeter cubed. Or you could have said rho equals 1.07. Well, first, I guess we have to convert, right? So basically, I need to convert that to meters, right? So I would do 100 centimeters to 1 meter, and I would do that 3 times, right? And so I would end up with 1,070 kilograms per cubic meter, like that. Okay? So there you go. Either one of those is acceptable. Okay, and now we need S, and the definition of S is the density divided by the density of water. So S equals, well, this density is 1066.7 kilograms per cubic meter, and the density of water is 1,000 kilograms per cubic meter. Some of you might have ended up using like 9999. That would be fine. S in this case equals 1.0667. Okay, no units. So we would say S equals 1.07 to give them the 3 sig figs. Okay, so basically this one's going to be worth 5. This one's going to be worth 5, and this one's going to be worth 5. And I don't see that there's a lot of, room for partial on that one, really. I guess unless you screw up one of these and it causes you to, it chain reacts. But I think that's probably where we'll be. Okay, this one was worth 10 up here. All right, let's go over here, and we'll do this manometer problem. I love manometer problems. They always show up, always. Okay. The manometer contains benzene, mercury, kerosene, water, and air, as shown below. Okay, so let's, for the column heights indicated, what is the difference in pressure between the pipes? Okay, so PB and PA. So we're going to start at PA. I'm going to build my equation, right? So here I am on PA. I'm going to go down to here. So if we're going down, we're going to add, and we're going down in benzene, gamma benzene, times that 20 centimeters, which for now I'm just going to call HB. Okay, so this is HB right here, is 20. Okay, now I'm going to go from that point and go over here, and I'm going to go up in the mercury. So that up is minus gamma mercury, and that's going to be the HHG equals that 8. HHG. Okay, so now I'm in the kerosene. So it looks like I'm going to go up in the kerosene to here. Okay, so that's a minus gamma kerosene times HK. Now HK, it looks like we're going from 8 to 40, so this is going to be a 32 centimeters. Okay, so now I'm up here, and I'm going to go down in the water, right there. So I'm going to go plus gamma water, and I'm going to go H water. What is H water? It looks like the water is that full 40. HW. No, H water is not that full 40, is it? Okay, it looks like H water is 40, and then you come back up 14, so it's going to be 26. HW equals 26. Okay, and then we've got this air, and we'll go minus gamma air times H air, and that's what, 9. Yeah, it looks like that's 9. So this is H air, and that's going to get us to PB. Okay, cool. So the next thing we'll do, the very next thing is we notice that this is going to be really small. So we're going to ignore it. If you decided not to ignore it, that's fine. So let's see what we can do. So algebraically, I'm going to bring the PA over to the other side. So I got PB minus PA equals the rest of that stuff. So PA, or PB, minus PA equals the rest of this stuff. Right, now for each of those gammas, what I'm going to do is I'm going to turn gamma B into SB gamma water, HB minus, and then for that gamma HG, SHG gamma water times HHG minus, I'm going to take that gamma K and make it SK gamma water, HK. And then we got the gamma water, which, doesn't need a specific weight. Okay, and there's our, that's basically our solution at this point. We're just going to be plugging numbers in there, and sorry, I have to squeak the chair. I'm wondering if y'all can hear that the whole time I'm doing these things. So what I'm going to do here, because it makes it easier to write this stuff out, and you'll see this on the key that I'm going to produce, is I'm going to write it like this. I'm basically going to pull out that gamma water because I don't feel like writing it 500 times, or really 4 times in this case, like that, and then I'm just going to put the gamma water out front. Okay, and that's just kind of a nice, easier way to write it out. So I'm going to keep on going, and I'm just going to start filling this in. I'll plug and chug. So S benzene is 88, 0.88. The HB is 20 centimeters. Okay, remember we need this in meters. Okay, minus SHG. What's SHG? 13.6. Okay, times the HHG, which is 8. Okay, and then let's see here. We got kerosene minus, where's the kerosene? Oh, yeah, sorry, 0.82. 0.82 times, maybe I'll put the minus right here so we don't screw it up. And the HK is 32 centimeters. Okay, and then water. Okay, so plus gamma HW, which is 26, 0.26 meters. All right, and then we'll close that, and then we'll do this gamma water, which is 9810 newtons per meter cubed. All right, so now that we have all these numbers in here, this is a plug and chug game, so I'm just gonna, fill this out for you. Okay, yeah, so I just basically multiplied all the numbers together. So keeping this on the outside and then distributing it to give these values. And then, maybe you should just pause it if you want to, check those in your calculator. And then adding them all up, I get a negative 8,969.9 pascals. So I should probably, bring this to 3 sig figs. And the easiest way to do that is negative 8.97 kilopascals, right? Because a Newton per meter squared is a Pascal, and so we're going to make this a kilopascal. Okay? So that's how we do this. As far as grading this one, basically we're looking at this. Let's see here. We're looking at this equation right here. So we're going term by term. So this is really the equation we're looking at right here. And I guess really, I could do it there, but I'm going to do it here, so I'm making sure that you're getting the right numbers. And so basically it's 2 for this, 2 for this, 2 for this, 2 for this one. And then, I mean, obviously including this in there. If you use something else, that will be an error. And then there's +2 for air, right? So if you, for either calling it a 0 and just moving on with your life, okay, or if you actually wanted to use the really small specific weight or specific gravity that it gave you. Okay. Obviously, anywhere in between there and here, you could have had an algebra error or something like that, in which case you'll lose points, and you'll see, like, I'll write something on there like algebra -1 or calculator failure -1, ooh, 1, you know, or something, not -0. I hope I never write -0 on anybody's. That's just like showing a real love affair with correcting people when they're not wrong. All right, so anyway, a cylinder is falling at a constant rate of whatever. Oh, wait, so I guess I'll hold for this one right here. Come on. Let's go ahead and let's erase these because clearly we don't, well, we didn't have, I hope I didn't have any errors. So this is a 10-point problem. So when it lets me write again, it's taking its sweet time, your frozen jerk computer. So we're going to, come on. Okay, so here, this one's worth 10. Okay, that was the 10 right there. Rocky does not like skateboarders, so he might bark in a second. Okay, so we've got this cylinder, and it's sliding down in this thing, and we've got all this stuff going on. And so I know right off the bat a few things that I'm going to have to do. So I'm going to create, like, some asides. I love asides, as you guys may know. So the asides that I'm going to do right here is I'm actually going to zoom way. You know what? Let me do a little tiny aside, right? So I can zoom all the way in here if I want. I'm going to do an aside right here. Okay? And what's going on right here is this, you know, this thing, this wall is not moving, and this quote-unquote wall is. So we're getting a velocity profile that looks like this, right? So I know already that this is that I'm going to need to figure out what this is, okay? Because that's going to be an important part of this problem. So here's the aside as I'm seeing it, right? So the du dr, it tells me to assume that it's linear. Assume a linear velocity profile. So I can make this the change in u and the change in r. Well, the change in u, I'm going to have to basically make a decision. You know what I want to call that. I'm going to call this side, let's say the velocity equals the u of the speed of the cylinder. And on this side, the velocity is 0. Okay, so the change in u from one side to the other, that's the u of the cylinder. Okay, now I need the distance from one wall to another, the delta r. So from here to here, what is that distance? Delta r equals what? Okay, and I already know, like, I haven't graded these yet. I'm about to start this evening. But I already know that this is going to be probably one of the most missed things on this exam. And so if I zoom all the way out, we can see that little d is 100 millimeters, big D is 100.4 meters. So if I zoom all the way in, that means from here to here is 100 millimeters. And from here to here is 100 millimeters, which means this gap right here is 0.2 millimeters because this gap right here is 0.2 millimeters. Okay, that's going to be the biggest missed thing. So that's what is going to go on the bottom there. So it's going to be 0.2 millimeters. Okay. All right, so that's the du dr if we zoom all the way in right there. Okay, the other aside that we're going to need, and this is a geometry issue, is I'm going to need, you know, the area that's rubbing or whatever is being pulled on by the fluid around it is this outside area here. So I need to know what that area is. Okay, so what I'm going to do is I'm going to say, well, what's the area of the outside of a cylinder? I should do this in blue, shouldn't I? Area. Okay, well, that area, let's see here. If I were to imagine cutting it right here, just like I had some scissors or something, and I was able to cut this tube right there and I unroll it, well, then it's a rectangle, right? If I unroll that thing. And it's a rectangle, so that the units of the rectangle would be the perimeter of this circle, right? Because that would be one side of the rectangle. So let's call that, I don't know, perimeter P. or circumference. Let's do capital C, circumference. Okay, circumference. And then we need to multiply times L, so that's the area of a rectangle. However, the circumference in this case, well, that's going to be pi times this little d right here. So this area is going to be pi times little d times that L. Okay, so that's my area. Okay, so those are my asides. This is another aside. All right, and I know I shrunk them way down, but that's okay. I'm going to remember them, and you can check those if you like. So what I'm going to do then for the rest of this, I'm just going to keep those in my back pocket because I'm going to use them in a second. But what I'm going to do is I'm going to say, okay, we've got this cylinder, and it's only got two forces on it. It's got weight going down, and it's got the force of friction, the force of shear going up. Okay? And I know, so this is my free body diagram. So I know then that because this thing isn't accelerating, I know the sum of the forces in the vertical is 0. So I can say F shear, or I should say sum of the forces in the Z direction equals 0. So F shear minus W equals 0. Okay? Well, the force of shear, well, that's tau, okay, the shear stress, times the area over which it acts, and a minus the weight equals 0. Okay? I'm going to expand tau by making that mu du dr. Okay, so that's tau. And then area, well, we just did this, right over there, and I said, well, that's going to be pi times the diameter, that's the circumference of the top, times the length, okay, minus weight equals 0. Okay, once we get here, I guess I should have made this, because it's linear, I could actually, right here, I could say, okay, well, let's make this delta U over delta R, right? So then when I plug all this stuff in, I'm just going to plug a bunch of numbers in here, 0.2 newtons times seconds per meter squared, okay, times, this is the U of the cylinder. What did I call that over there on my aside? Whoa, don't do that. I called that the U of the cylinder, yes. Okay, I apologize for the, that little messiness there. 0.2 times 10 to the negative thirds meters. Okay, that's going to be a common error right there, is forgetting that, we need to convert that to meters, or else we're going to get a wrong answer here. So then we'll do pi. The D is 100 millimeters, 0.100 meters. And the L is 200 millimeters, okay? Minus the weight, which is 15 newtons, equals 0, okay? Notice that we kind of need to use meters for all this because of this little one right here, okay? I mean, you could convert that and leave the rest in millimeters if you wanted to. I think that's a little bit more complicated than you might want to make it, but it's kind of your call. Okay, so we're going to plug all this into the calculator, and we'll get, okay, this annoying number. Okay, so the speed of the cylinder is that number, and, like I say, I prefer 3 sig figs, so you could do 0.239 meters per second if you like. I tend to go to 23.9 centimeters per second, just because that's like, I don't know, a little bit easier for me to think about, but, whatever floats your boat, okay? So as far as how do we grade this one, so we will go up here and we'll say, okay, so the first thing I want when I'm checking your work is I want to know that you understand this concept right here, that this thing is not accelerating, that there's a force balance here. If I can see some sign of that balance in there, then you get 2 points. Then once we get down here, I'm looking kind of at this equation right here, and let's see, did you plug that in the right place? Did you get this area right? That's worth 2. Did you get this shear right? That's worth 2. And did you plug the viscosity in where it belongs, right? And so that gets us to 9, and then the answer is worth 1 more. Okay, so that's the 10 for this problem. Okay. Test is beginning to look cool. Okay, so now we're going to go over here to this one. A room in the lower level of a cruise ship. And this problem, I think, for me personally, I thought this was an easier problem than is typical. We could have gotten some much harder ones. So just, kind of be aware of that going forward. Okay, so I'm going to work on this one. So basically, I don't know that I've ever been on a cruise ship that had well, I've only been on one cruise ship, but I didn't know they had windows underwater. That'd be super cool. Maybe a little terrifying. Anyway, so here we go. So the way I always work these forces on a on a thing or whatever is I think about the shape of the gate. Okay, and in this case the shape is a circle, right? And it's got a diameter of 45 centimeters. That's an annoying number. If I do this again, I will change that number, 0.45 meters, because I don't, 4.4 would have been just so much easier, right? Anyway, so like what I always tell you guys is that we need 4 quantities, and last is the area, right? Okay, so the HC is the depth, straight down to the centroid, so that's going to be 2 meters. Okay, the YC is the depth from the surface down to the centroid using along the gate, so that in this case is the same, so that's going to be 2 meters. Okay, the I, if we look it up in your fancy, handout, I for a circle is pi r to the 4th over 4, so pi r to the 4th over 4. So that's going to be pi times 0.225 meters squared over 4. That's going to be an awfully small number. I hate calculating moments of inertia because they don't really make a lot of sense to me. Like I'm going to get a number and I'm like, is that reasonable? And of course I really have no idea, and that's what I don't like about them. Oh, sorry, this should have been to the 4th, shouldn't it? We'll multiply that number times pi and we'll divide by 4. And it looks like my key and I are currently in agreement, which is always nice. Okay, and then we'll do the area, and of course the area is pi d squared on 4. You could have used r if you like. You'll get the same number. So the diameter in this case is 0.45 meters squared on 4. Okay, so now that we've got, this kind of like, almost like formulaic work, right? Nothing really interesting has happened so far. We're going to start solving for the things that we want, So the first thing I want is the hydrostatic force acting on the window. So that I typically call the force of pressure. And that is going to be the gamma of, in this case, what is it, seawater? Seawater times HC times the area. So the force of pressure equals, well, the gamma of seawater, that's 1.03 times 9810 newtons per meter cubed, times HC, which is going to be 2 meters, and the area, which is right here, so 0.15904 meters squared. So the FP equals, 3214 newtons. Noticing, of course, that meters cubed cancels with meters and meters squared. Okay, so that gives us the units that we wanted. So we have to feel at least a little bit okay with that, right? Now, of course, we want 3 sig figs, so I always like to convert it to something that looks pretty, right? Because I could have done 3,210 newtons, and that would have been fine, but I like it like that, okay? So the second question is, where does that force act relative to the water surface? Okay, so that's the YC. It could be the HC, the HCP, it's the YCP. And it could be the HCP if such a thing existed, because in this case, they're both vertical. So we're just going to go ahead and solve for the YCP. So the YCP equals the YC plus moment of inertia, area moment of inertia, divided by the YCA. Okay, so let's see here. YCP equals the YC, that's 2 meters, plus the I, 0.0020129 meters to the 4th. Man, it's annoying keeping 5, isn't it? And the YC, 2 meters, and the A is 0.15904 meters squared. Okay, so we're going to get a YCP, and 2.0063 meters. So with 3 sig figs, like no one wants that, 2.01 meters or 201 centimeters, whatever kind of floats your boat. All right, so how would we grade these suckers? Okay, so each one of these is worth 5 points, so we need to figure out what we're going to do, 1 point for each of the kind of things in this. So we'll make this area worth 2 points, this HC worth 1, and this density worth 2 points. Okay, so we'll go over here, and for this one, let's see, how do we do this here? I think we're going to make this worth 1, this is going to be worth 2, This will be worth 1, and this will be worth 1. Okay, and so that'll be 5 points right there. 5 points here, 5 points here for a grand total of 10. Okay, and if we zoom out, that means we got 10 on this page, 20 on the page before it, and 25 on the page before that. So 10, 20, and 25. So what's that, 30, 40, 55, I believe? So this is a 55-point exam. And hopefully I just got a 55 out of 55. But I cheated. I made the exam. 25, 45, yes, 55. Okay, so hopefully that is helpful. And yeah, so that's 30 minutes. So yeah, take it easy, and then I hope this helped you guys. All right.